We will discuss some definitions of abstract algebra. So ideal की definition देखते हैं. A non-empty subset U of ring R is said to be ideal or two-sided ideal of R if it satisfy U is a additive subgroup of R, small u belongs to U and small r belongs to R, then R U and U are in U. Left ideal की definition: a non-empty subset U of ring R is said to be left ideal of R if it satisfy the two conditions. First one is U is additive subgroup of R and small u belongs to U and small r belongs to R, then R U belongs to U. It is it's said to be left ideal group. Now definition of right ideal: a non-empty subset U of ring R is said to be right ideal of R if it satisfy U is additive subgroup of R and U belongs to U and R belongs to R, then U R belongs to R is called right ideal of R. Now there is another definition of principal ideal. An ideal S of ring R is said to be principal ideal if there exists an element small a belongs to S such that any ideal T of R containing A also containing S is that S is equal to A. Thus an ideal generated by a single element of itself is called principal ideal. Maximum ideal: an ideal S is not equal to R in a ring R is said to be a maximum ideal of R if whenever U is an ideal of R such that S is a subset of U is a subset of R, then either R is equal to U or S is equal to U. Now there are some example related to ideal. So the first one is prove or show that I phi is an ideal where I phi is equal to kernel of phi. To prove that I phi is an ideal, we have to prove that two conditions. First one is I phi is an additive subgroup of R. I phi is a subgroup under addition. And the second one, if X belongs to I phi and small r belongs to capital R, then XR, Rx belongs to I phi. If X, Y are in phi, then by definition of kernel of phi, phi x is equal to 0 and phi y equal to 0. Thus, phi x plus minus y is equal to phi x plus minus phi y, which is equal to 0 plus minus 0 is equal to 0. So, phi x plus minus y is equal to 0. Then x plus minus y belongs to I phi. Since I phi is a subgroup, now if X belongs to I phi and small r belongs to R, then phi x is equal to 0. So phi xr is equal to phi x dot phi r. So 0 dot phi r is equal to 0. Then it implies that phi r belongs to I phi. Similarly, phi rx is equal to phi r dot phi x, which is equal to 0. So this implies that rx implies Rx belongs to I phi. Now there is another example. If U is an idol of R with unity, and then U is equal to R. If U is an idol of R, so its subgroup of R it is subgroup of R under addition. And U is a subset of R, which is equation number 1. Now X by any element of R, X belongs to R, 1 belongs to U and X belongs to R, so 1 dot X belongs to U, then X belongs to U. R is a subset of U, so R is a subset of U, which is equation number 2. From equation number 1 and equation number 2, we get U is equal to R. Now there is another example or a theorem. Intersection of two ideals is again an ideal. Proof देखते हैं इसका. Let U1 and U2 be two ideal of R by the definition of ideal, u1 and u2 be additive subgroup of R. Small r belongs to capital R. Now we have to show that u1 intersection u2 is an ideal. Let u belongs to u1 intersection u2 and r belongs to R. Small r belongs to capital R. Then small u belongs to u1 intersection u2 and ur belongs to u1 intersection u2. मतलब आर यू और यू आर दोनों ही u1 इंटरसेक्शन u2 में बिलोंग करते हैं. देन आर यू कॉमा यू आर बिलोंग्स टू u1 intersection u2. Since u belongs to u1 and u belongs to u2, so u1 and u2 are ideal of R. If small r belongs to R and u belongs to u1, so ru belongs to u1 and ur belongs to u1. If small r belongs to R and u belongs to u2, so ru belongs to u2 and ur belongs to u2. Then ru belongs to u1 intersection u2 and ur belongs to u1 intersection u2. u1 intersection u2 is an ideal. There's another definition. The ideal 0 and R of ring R are called improper integral. Other are said to be proper integral. There is another theorem. If u and v are ideals of ring R, then u plus v is equal to u plus v, such that u belongs to u and v belongs to capital V is an ideal of R. इसका proof है, let x comma y belongs to u plus v, which is capital, and x is equal to u1 plus v1, y is equal to u2 plus v2, where u1 comma u2 belongs to u and v1 comma v2 belongs to v. Then x plus minus y is equal to u1 plus v1 plus minus u2 plus v2. So u1 plus minus u2 plus v1 plus minus v2. So u plus v. X plus minus y belongs to u plus v. So u plus v is additive subgroup. Now if x belongs to u plus v and if x belongs to u1 plus v1, if u1 belongs to u and v1 belongs to v, if small r belongs to R, then xr is equal to u1 plus v1 r, and which is equal to u1 r plus v1 r, which belongs to u plus v. Therefore u1 belongs to u and r belongs to R. U is an ideal, so u1 r belongs to u. Similarly rx belongs to u plus v, so u plus v is an ideal. Now there is another theorem. If u and v are ideal of A of a ring R, then uv is equal to small u small v, such that u belongs to u and v belongs to v is an ideal of R. इसका प्रूफ है, let x comma y belongs to uv, then x is equal to u1 v1 and y is equal to u2 v2, where u1 comma u2 belongs to u and v1 comma v2 belongs to v. Then x plus minus y is equal to u1 v1 plus minus u2 v2. So u1 plus minus u2 dot v1 plus minus v2. Since u1 belongs to u and u2 belongs to u, so u1 u2 belongs to u. Similarly v1 belongs to v and v2 belongs to v, so v1 v2 belongs to v. Then x plus minus y belongs to uv, hence uv is an additive subgroup. Let x belongs to uv, so x belongs to u1 v1. If r belongs to capital R, then xr is equal to u1 v1 r, so u1 r v1 r, which is equal to u dot v. u1 belongs to u, r belongs to r, u is an ideal, and u1 r belongs to u. Now similarly xr belongs to uv and similarly rx belongs to uv, so uv is an ideal.